The paper discusses the use of a bidirectional long short-term memory (BiLSTM) model for accelerating drug safety assessment. This model processes input molecular sequences in Simplified Molecular Input Line Entry System (SMILES) notation to understand sequential patterns and predict toxicity and solubility of molecules. The BiLSTM model is a variant of Recurrent Neural Network (RNN) that processes input sequences from both forward and backward directions. It surpasses previous approaches such as Trimnet and Pre-training Graph neural networks (GNN) on the ClinTox dataset with a ROC accuracy of 0.96 and outperforms previous models on the FreeSolv dataset with a low RMSE value of 1.22 in solubility prediction. The paper also highlights the importance of computational methods in accelerating drug discovery, particularly in the phase of lead optimization where absorption, distribution, metabolism, excretion, and toxicity properties of lead compounds are assessed. The research paper discusses the application of neural networks in QSAR for predicting toxicity and solubility of new lead compounds. It proposes a model that uses the QSAR approach, training on known compounds data, and employs recurrent neural networks, RNNs, specifically BiLSTM, for processing input sequences. The model's input is encoded into binary arrays and fed into the BiLSTM layer, which processes the data bidirectionally. The output is then passed through a dense network equipped with a sigmoid function to predict toxicity. The paper also delves into graph-based methods, highlighting the use of graph convolutional layers and fully connected neural networks for molecular property prediction. It emphasizes the importance of understanding molecular structures and their relationships for toxicity prediction. The summary covers key concepts, methodologies, and significant findings from both pages, providing a comprehensive overview of the research. The proposed model utilizes long short-term memory (LSTM) networks to predict molecular properties, specifically toxicity and solubility, for molecular structures represented as SMILES sequences. The architecture consists of 3 layers: an embedding layer, an LSTM layer, and a dense layer. The embedding layer converts each SMILES sequence into a dense vector representation, which is then fed into the LSTM layer. The LSTM layer processes the embedded sequences, capturing dependencies and patterns within the data over time. The final dense layer performs classification based on the LSTM's output, predicting the toxicity label. The LSTM cell's gates, including the input gate, forget gate, and output gate, are analyzed by giving values into the equation, as depicted in Figure 2. The gates are sigmoid activated, ensuring gate values fall within the range of 0 and 1. The update cell state and hidden state are determined using the equations, which involve the cell state, hidden state, and input gate. The Bidirectional-LSTM (BiLSTM) architecture is also explored, which passes information bidirectionally, capturing both past and future dependencies in the SMILES sequences. The BiLSTM layer consists of 2 LSTM networks, one processing the input sequence in the forward direction and the other in the backward direction. The hidden states from both networks are combined to obtain the final output, predicting molecular properties. The loss function calculates the discrepancy between the predicted outputs and the ground truth labels, providing feedback to the model on how to adjust its parameters to minimize this discrepancy. The complete flow from inputs to output is shown in the architecture figures. The use of BiLSTM allows the network to understand the context of each character, token based on its surrounding characters, tokens, enabling more accurate predictions of molecular properties. The research paper discusses the application of a sequence-based approach for predicting molecular solubility using a BiLSTM model. This model captures complex relationships between molecular structures and solubility, leading to significant advancements in predictive performance. The architecture of the BiLSTM model, as shown in Figure 4, enables the model to capture information from both past and future contexts, which can lead to better performance. Comparative analysis demonstrates the effectiveness of the sequence-based approach in solubility prediction. BiLSTM models trained on SMILES data outperform traditional methods, yielding superior prediction accuracy and efficiency. On the ClinTox dataset, the proposed model achieved a ROC accuracy of 0.96, surpassing other models like Trimnet. Similarly, on the TOX21 dataset, the model achieved a ROC accuracy of 0.81, outperforming graph-based methods and GAN models. When performed on synthetic data, the model achieved an ROC accuracy of 0.80. The proposed model also outperforms the previous best model GLAM with a lower RMSE value of 1.2 compared to GLAM's 1.31. This indicates the better predictive performance of the proposed model. A comparison with a few machine learning algorithms is shown in Figure 3, further highlighting the effectiveness of the BiLSTM model. The findings suggest that the sequence-based approach using BiLSTM models can significantly improve molecular solubility prediction, which is crucial for drug development and discovery. The limitations in future work include the need for more diverse datasets to further validate the model's performance and potential improvements in model architecture for enhanced accuracy. The research paper discusses the application of sequence-based approaches, particularly BiLSTM networks, for enhancing solubility and toxicity prediction efficiency in drug discovery. The proposed model leverages SMILES information to provide a more accurate and streamlined approach compared to traditional methods. Through hyperparameter tuning, the model achieved better ROC accuracy with specific parameters. The paper highlights the potential of sequence-based methods in advancing computational drug discovery techniques and underscores the importance of incorporating machine learning approaches in predictive modeling tasks. It also explores the use of deep learning methods for toxicity prediction and discusses the limitations and future work.